We've studied a number of cases where the integral we looked at had an obvious infinity in it, because it was actually in the question. We were integrating up to the infinite interval as our upper limit. Now, there are other infinities that can creep in, and we'd call that something like an implicit infinity. And that's when the integrand, which is the function inside your integral, if it goes to infinity at the edge of your interval. So let's take a look at some examples like that. Let's consider the integral from 0 to 1 of 1 over root x. And think about what this looks like. 1 over root x is one of these graphs that has the asymptote at 0 and goes off to infinity, or goes down towards 0 as you go to infinity. And if we're talking about the area from 0 to 1, then we're actually talking about capturing this vertical asymptote in the interval. And you can go back a few pages and find the definition we use here, but I think it makes more sense to look at it in context. Here we have something that doesn't look like an infinity, but this combination of the 0 limit and plugging 0 into here, giving us an infinite value or an undefined value. There's something fishy here, and so what we have to do is integrate not to 0, but to some other value, a, and we leave the integral the same. And this translates in a picture to the following. We've got our graph, here's 1. What we're going to do is cut the interval off at some positive value a, and then we're going to push a down towards 0 so that we find the area first, that's the integral here, and then we're going to take that lower limit of integration and push it down towards 0 and see what happens. And so we'll do that here with a limit out front. A is going to go to 0, and usually this makes very little difference in practice, but think of the values that make sense for a. If the problem's at 0, a better be at the right, and then it better head down towards 0. So it's going to head towards 0 from the right, which we used to call, or in last term, a limit as 0 approaches from the right, 0 plus in the limit phrasing. Okay, so that's the only real change, and in fact it's the same thing we did before when we had an infinite limit in the other direction. We just have to be a little more self-aware as we do these problems that there is an infinity lurking at one of the limits here. Okay, once we get to that realization, the procedure is identical. We're going to copy our limit because we can't evaluate it yet. A is still this mysterious part of this larger calculation right now. But what we can do here is rewrite this as x to the negative 1/2. Then if we integrate it, we're going to get x to the 1 higher power, positive 1/2, divided by the new power, evaluated at 1 and a. We're going to copy this limit out front again. We always keep it around until we can evaluate it. And dividing by 1/2 is like multiplying by 2. Then we have 1 to the 1/2 minus a to the 1/2. And these limits with zeros tend to be easier than limits with infinity. The half is just square root, so we could call this square root of 1. That's just 1. And that's square root of a. And well, what happens is we plug in positive values into a that get closer and closer to 0. We get 0 at the end. So this square root of a approaches 0. What does that give us overall? A total area of 2. So this area here that's been sketched out, that area equals 2 square units. Even though there's an infinite part to it, that branch narrows quickly enough that the overall area is going to be finite. Let's look at a contrasting example to see what other kinds of things we can find in these kinds of problems. We're going to integrate again from 0 to 1, and we notice that same problem, that when 0 is our limit, the function actually isn't defined there. Why is that? Because we have a nice vertical asymptote again, same basic shape for all intents and purposes. We're going to go up to 1, but the 0 is where the asymptote is, so we are going to cut first at a and then push a down towards 0. So we're going to apply our definition for an improper integral. Split this poorly defined question into two well-defined parts. That lower limit we're going to call A. That's our lower boundary, and then we're going to push it afterwards down towards 0. The upper limit stays the same, and we have our integral there. Integration's easier if we write it as powers. So we take the limit as A goes to 0 from the right of x to the minus 2. Integrate that, we get x to the minus 1 over the new power between 1 and A. Copy the limit, and we get negative x to the negative 1 is 1 over, so 1 over 1, minus negative 1 over the other limit being imposed. And that we can rewrite one last time as minus 1 plus 1 over A. Okay, now we're at a stage where we can ask what happens to that expression as A approaches 0, and here we have A in the denominator. So 1 over smaller and smaller, smaller and smaller numbers, this whole thing is going to head off towards infinity. If we don't get a nice finite number out of this, all we can really say is that this integral diverges. And if this integral diverges, that's about all we can evaluate, but it means that the area underneath this graph, 1 over x squared, is infinitely large. Notice, if you're someone who likes memorizing rules, this is the opposite of what we learned before when we had an infinity in the exponent. If we had limit of integration. When we had an infinity up here, the integral of 1 over x squared, which is this branch of things, the integral converged, we got a nice finite number. But if we approach the other way and take the vertical asymptote side, it turns out we get an infinite area. There's good reasons for that, between the relationship between 1 over root x and x squared, and this branch versus that branch as being inverses. Suffice it to say that this calculation will never lead you astray. You'll always get what you expected out of it. It'll tell you, if you can evaluate your limit correctly, whether you get a nice number for the area, finite convergent integral, or something like this case here, where the limit clearly diverges as we push this boundary down towards 0. This grows off to infinity, so we get a divergent value overall.